result. Okay, so actually not going to tell you about lab and the fact that I work with Jack and I work with Liam, but I'm not going to talk about any of that. I'm going to tell you about a project I've been working on with Mark Toussaint and some of his students about task and motion planning. Okay. So task and motion planning is a very difficult problem, and if you were tried to solve it, probably know this. You've got some sort of decisions, tree of decisions you need to make. So maybe you start with picking a logical plan. So I'm going to pick up block A, I'm going to stack A on B, and then I'm going to pick up block C, etc. Right? But if you're doing task and motion planning, then that's not enough, right? Because you need to come up with a trajectory that implements this high-level plan. So maybe you start with picking a set of waypoints. This is the grasp for picking up A, this is the grasp for the stack, etc., right? But that's not enough, right? Because you need to find a collision-free path between the waypoints, right? And maybe there isn't one. And finally, you want to compute the joint motion. And so you pick a logical plan using A star, and then you find waypoints using maybe nonlinear programming, doing a drag drop, and then a collision-free path you solve using RT, and then you do the final optimization using, again, a nonlinear programming, and you get a cost of 7 for the plan, right? Except that this is not the only option, right? So first, solving each of these nodes has a computational cost, right? Solving the nonlinear program, finding a plan, etc. So maybe this costs 2, this costs 4, this costs 7, right? And this costs 6. So to find a solution that gives you a cost of 7 takes, I don't know, sum these up, 19 computational time units. But it is not the only option, right? So you're actually searching in a tree of possible computations, which will end up giving you different motions. And each of these may have a different computational cost and a different cost for the plan you find at the end. And what's even more challenging is that some of these computations take time, and maybe you want to stop this computation in the middle, right? You haven't solved this nonlinear program, but you're saying, oh, this is taking too long, we're going to move to the next one, right? So you have to reason about interrupting computations, right? And then finally, some of these nodes have an infinite branching factor, right? How many solutions are there to this nonlinear programming optimization problem, right? I don't know, maybe there's an infinite number of them. So this is much more difficult than the typical search tree you may have seen in Introduction to AI, right? Because you've got an infinite branching factor and computations to interrupt. So I won't go into too many details. This is what you don't want to do, right? What we want to do is we want to keep things stupid and simple. And basically we want our search algorithm to make the algorithmic decisions for us. And we want the algorithm to decide where to invest the next unit of computation time, okay? So we came up with a very, very simple idea. We call it effort level search. It's basically a blind search, except it's not just blind search on the width, like a standard BFS. It's a blind search that balances going deep, going wide, and investing more compute, okay? So basically for each node, the cost of the node is how much computation I've invested in this node so far, and what is the order of this node in the successors of its parent. So the first node costs 1, the second node costs 2, etc., right? And then the cost of a path is the sum of the costs of, the cost of a client, is the cost of the nodes along the path. So basically, you penalize spending too much time on a node, you penalize going too wide, and you penalize going too deep, right? So by doing basically starting an openness based on this, you get something which balances all of these different dimensions. So this is effort level search, and of course, you can complicate things. This is just an example. Instead of just having these simple numbers, you can do these weird transformations and get this. It doesn't affect things too much. but it does allow you to simulate the budgeted bandits and things like that. Essentially, right, it's just a breadth first search, except it's over infinite search. Okay, so, well, surprise, surprise, it works. Based on, all of these benchmarks. Yeah, so basically, this is a new way to search for trees with an infinite branching factor. And of course, this is a blind search. So I've got one student now working on better search guidance based on historical data. If you're interested in other ideas, feel free to talk to me. Except I won't be here next year, I'll be on sabbatical. But you can still talk to me. Thank you.